So what we want to look at now is double integrals, right? Your topic of double integrals. It's your notation for a double integral would be the general notation for double integral is this over here, right? Okay, so what you have is you have a function of two variables, f of x, y. Okay, and what you're going to be doing is you're going to be integrating over region R, right? And this region R is a region R in the xy plane, right? Okay, so before I get into this, let me remind you about the situation of just integration of a single variable, right? So a normal definite integral. Okay, so this is an example over here of integral of a single variable. Right. Okay, so what I'm doing over here is I'm integrating a function of a single variable, right? In this case, your function is equal to x squared, right? And I'm integrating this x squared between your limits 3 and 2, right? 3 and 2, and you all know how to integrate this. You get x cubed on 3 and then you substitute the values 3 on 2. So I'm not going to get into how you actually evaluate this. This you should know how to do already, right? Okay, but the point, this is a definite integral, right? And this over here is a specific definite integral where you're integrating the function x squared between, okay, so you're integrating the function x squared, and the x squared is represented by this graph over here, right? So y is equal to f of x is equal to x squared is the graph of that function is this parabola here, and you integrate in between limits a and b here, right? Okay, and when you work out this integral, you get this answer, which is 6.33, right? And that area, this value over here, this 6.33 is equal to the area under the curve, right? Right, so, well, what do I mean by area under the curve, right? What you have is, you have, first of all, you have your graph over here of the function, and the graph is y is equal to f of x, right? So the graph is y is equal to x squared. Right, so your graph is y is equal to x squared here, right? And you integrate in between limits 2 and 3, right? So you have your limits down here. A is equal to 2 and B is equal to 3, right? Okay, so what you want to focus on is you want to focus on this horizontal line here, right? This is a line segment between 2 and 3, right? And what you're doing is you get in the area between uh, this line segment 2, 3 and this graph over here, okay? I mean, you all know how to do this already, but I want you to look at it in a certain way, right? So you have your graph y is equal to f of x, right? You have this line segment down here that's formed from your limits of integration, right? Your lower limit of integration is 2, your upper limit of integration is 3. You have this line segment over here. And the area, what you want to do is, okay, so once you have this line segment over here, you take your this corner over here and you go up with a vertical line like this, right? And then you take this corner over here and you go up with this vertical line over here, right? And what you get is you get an area enclosed by these lines and this curve on top over here, right? And that's this blue area. And this blue area over here, the actual area, is equal to the value of the integral, right? When you work out your integral here, you get this value 6.33, and that's equal to this area here, right? So this is nothing new, you would have seen this before. Right. Okay, so now what I want to do is I want to compare this situation here, right? This visual interpretation of a definite integral. I want to compare it to your interpretation of a double integral, right? Okay, so it's in fact similar, right? Your double integral here, right, has analogous interpretation to your normal integration, the integral of a single variable over here, right? Okay, so well, what did you use over here, right? What you used over here is you needed a graph of your function, and you were integrating over some region, some some interval that is downstairs on your x-axis over here, right? Okay, so you had your graph, and then you had some interval downstairs on your x-axis. Right, so likewise over here, right, what I'm going to have is my graph, right? I have my function of two variables, and what I'm going to have is a graph for that, right? Now, we talked about this, a graph, a function of two variables would form a surface for you in three-dimensional space, right? So this light gray surface over here is a graph of a function of two variables, right? Okay. Right, so the graph in the case of a function of two variables is a surface, right? The graph in the case of a function of a single variable is just a curve, right? Right. Now over here, what I'm doing is I'm integrating over this interval a to b here, right? This line interval going from 2 to 3, right? In the case of a double integral, what you're going to be doing is you're going to be integrating over a region down in your xy plane here, right? Okay, and this particular example, what I'm doing is I'm integrating over a region that is rectangular in the xy plane, right? Right, okay, so, well, what did I do over here to get this area, right? What I said is once you have this, so back to your single variable case, once I have this uh, interval over here, what I do is I take the corners, well, I take the entire thing and I project it up until it hits the graph here, right? So if you want this piece from here, the piece from here to here is in fact what you get when you take this AB and you push it up until it hits your graph, right? So it hits your graph over here, right? And then what you will, this uh, this integral of a single variable, right? The interpretation is the area of this region, right? Okay, so you had your interval down here, the form from the AB. You take this and you push it up until it hits your graph here, right? And you have vertical lines when you push up, right? And what you're going to have is an area enclosed by these curves, right? And this area is equal to the value of this integral. Okay, so we want to do something similar over here. I'm saying what I'm doing is I'm integrating over a region R in my xy plane, right? So what you're going to do is you're going to take this region now and you're going to push it up, right? And one easy way to see it is you just take the corners and you push up the four corners until it hits the graph, right? And you see the four corners, it's coming up on this, along this dashed line over here to hit at okay, it's coming up on, so this corner over here will come up and hit this corner, this point on your graph, right? Likewise, this corner over here will come up and hit this point on your graph, right? Okay, so this entire rectangular region, when you project it up, right, it will hit your graph, and it hits your graph in this dark gray region over here, right? Right. Okay, so, well, now what I want to do is I want to interpret my double integral, right? Okay, so your double integral, what you're doing is you're integrating a function of two variables, right? And your function of two variables, you can graph it, right? When you graph it, you get a surface in a three-dimensional space, right? Okay, and then when you're doing a double integral, you're integrating over a region R in your xy plane, right? In this case, the region is rectangular, so you have your region down here, right? And now what you do is you could take this region and project it up, right? And when you project it up, it's gonna hit your graph over here in some surface, and the surface is this dark gray area here, right? Okay, now if you notice this over here, this is basically a box, right? It's more or less a three-dimensional box where your bottom face is this rectangular region. Then you're going to have, so this is one side of your box, and then you're going to have four vertical sides, and then finally you're going to have this top over here, right? Now the top over here isn't quite flat, right? So this isn't strictly speaking a normal, say, a normal three-dimensional rectangular box, right? What it is the top over here, the top of your box is formed from your graph here, right? But anyway, so once you have that, right, what you want to realize is that this three-dimensional box over here, right, you can consider the volume of it, right? Okay, so it's basically like a rectangular box, except probably this top over here is just sort of distorted according to what the graph is, right? And the volume of this region over here, right, is equal to your double integral, right? Okay, so what I'm saying here is that any double integral, right, you can interpret as a volume, right? And then in order to interpret it as a volume, what you need to do is for your function over here, you will need to graph the function, okay? And you'll need to sketch a region in the xy plane, right? And once you sketch the region in the xy plane, you push it up until it hits the graph, okay? And then what you'll get is you'll get a three-dimensional region here, right? Three-dimensional enclosed region. And the volume of that three-dimensional enclosed region is equal to the value of this double integral, right? So a double integral has an interpretation as volume, right? And that's similar to the case of, or analogous to the case of integral of a single variable, where integral of a single variable was equal to area under the curve. Right, okay, so here's our next graphic illustrating the interpretation of a double integral, right? And so you have your function of two variables over here, right? So in order to interpret this as a volume, the function of two variables, you'd need to form the graph, right? So the graph is z is equal to f of xy, right? And here, what they call in, what I call the region R, they actually call D, right? But it's the same thing, right? Same idea here. Okay, the difference, one difference over here is while I use a rectangular region, they just, over here, they're using a general region, okay? Okay, right, so you want to do a double integral. Okay, so you want to evaluate this, you want to interpret this double integral over here, or a function of two variables over a region, and here they call it D, right? Doesn't make a difference what you call it, right? You call it, this is called over region D in the xy plane, right? So the region D is specified for you, alright? So if you want to interpret this as a volume, right, first thing you want to do is you want to sketch your region down here, D in the xy plane, right? And you'd also want the graph of your function, right? And the graph of your function, which is this blue surface here, forms a surface in three-dimensional space, right? So this is the graph of your function. This is the region D down here in the xy plane, right? And this double integral is equal to the volume between this region D and the graph of your function, right? So you could think of doing the same thing, right? You have your region D and you just take this and you project it up, right? You project it up until it hits the graph, right? And what this gives you is this gives you a three-dimensional enclosed region, right? So some sort of region over here, some sort of three-dimensional region, which is enclosed, right? It's enclosed by, say, this curved surface that's wrapping around over here, and it's enclosed by a flat region, a flat face down on the xy plane, and the top over here is coming from the graph of your function, right? So this is some enclosed volume over here, and the actual volume is equal to this double integral. Right, so we saw interpretation of a double integral. Now we want to start looking at how to actually calculate the double integral, right? How to work it out. Okay, so the first thing that we would need, okay, so something that we would need would be something called partial integration, right? Okay, so let's just do an example of partial integration. So I have this function of two variables over here. This is x, y, right? And notice here I'm integrating with respect to y, right? Right. So when I'm integrating this expression, this xy, with respect to y, right? The x is just going to be a constant for me, right? You just treat the x as a constant. So this is why you call it partial integration. It's similar to the idea of partial differentiation. Partial differentiation, what you do is if you differentiate and say with respect to y, you treat the x as a constant, right? So likewise for partial integration, if you're integrating with respect to y, you just treat you integrate the y over here and you treat the x as a constant, right? Okay, so if you integrate the y here, right, you integrate in y with respect to y, you just use your power rule over here, so you're going to get y squared on 2. And then the x will just come along as a constant, right? Okay, and then once you do that, right, what you need to do is you need to put in the values, right? Now, if you integrate in here with respect to y, right, it's understood that these here are y values, right? These are not x values, these are y values, right? So once you do integration here with respect to y and you get the y squared on 2, what you need to do is you need to put in your limits, right? Normal way that you do integration, right? And these here are y values, right? Okay, so you put in y is equal to 1 and y is equal to 2, right? And just as how you do it in normal integration, you put in the y is equal to 2 first. You put in the top one. So you'd get x 2 squared on 2, right? Which is 4x on 2, right? You put in the y is equal to 1, right? So you're going to get x times 1 squared on 2, which is x on 2, right? So this is 4x on 2 minus a half x, right? So you put in the y is equal to 2, you get this expression. You put in the y is equal to 1, you put this expression, and you do what you normally do, you subtract them, right? So here I have 4x minus x on 2, and what I'll get is I'll get 3x on 2, right? Okay, so that's an example of partial integration, right? Right. Right, so in this partial integration, just a couple of points. What you're doing is you're integrating a function of two variables with respect to one of the variables. And in this case, the variable that you integrate with respect to is y, right? You could also integrate with respect to x, but we will get to that, right? It's the same idea, right? Okay, so first thing is you have a function of two variables and you integrate it with respect to one of the variables, right? And if you decide that this is the variable that you integrate in with respect to, then what you do is you treat the other variable as a constant, right? So you notice here that we treat the x as a constant. Okay, and then the last thing that you want to notice over here is that this expression involved x and y, right? This is x times y, right? And when I integrated with respect to y and I put in y values, notice I no longer have any y in this expression. And this over here, I end up with something involving just x alone, right? So if I have a function of two variables and I integrate with respect to one of the variables, what's going to happen is after you do your substitution, the variable that you are integrating with respect to, which is y, right, is no longer going to be in your expression. So in a sense, what you're doing is you're eliminating one of the variables, right? Here you had xy, and now you just have something just involving x alone. Right, so how we're going to do a double integral, at least for a rectangular region, is Fubini's theorem, right? Okay, so this is if I want to integrate over a rectangular region R in the xy plane, right? Okay, so by a rectangular region R in the xy plane, I mean a rectangular region like this over here in the xy plane, right? If later on you're going to be integrating over regions, and this is when you project and you actually look down in your xy plane, right? We're going to be looking at more complicated regions than rectangular regions, which we'll call type 1 and type 2, right? And then last of all, the last region that we will look at would be something from polar coordinates. That's called a polar rectangle, right? So in this class, you're looking at for your double integrals, we're going to be integrating over 4 types of regions in the xy plane, right? First type of region is rectangular, right? Okay, so if you draw this just in the xy plane, it will just be a normal rectangular region, right? The other 2 types would be type 1 and type 2. And then the final type would be polar rectangles, which would be this type over here, right? Okay, and the method of integration that you're going to use, right, depends on the type of region that you have, right? So if it's rectangular, you'd use a certain formula, right? If it's type 1, you're going to use a certain formula. If it's type 2, you're going to use a different formula, right? Each of these formulae, they have elements in common, right? So it's the same idea that you're going to be using for each of these, right? Except that, well, the order and so would be different, and you need to keep track of some subtle differences and so, right? Okay, so this first method, this Fubini's over here, Fubini's theorem, right? This first one over here is for a rectangular region, right? So this is a rectangular region in your xy plane. A rectangular region in your xy plane. Example of what that looks like is this here, right? So this is a rectangular region. Right, so you have, this is your xy plane over here, right? And you have a rectangular region. Notice here the x is lying between 3 and 4, right? So that's what's said over here, right? The x is lying between 3 and 4, and the y is going between 1 and 2, right? Okay, so this is three-dimensional, right? So the region is projected down onto the xy. Well, the region lives in the xy plane over here, right? So what you're seeing is you're seeing this region R down here on the xy plane because of the perspective, and so it's a little slanted, right? But if you looked at a plan view, you'd see this as a genuine rectangle in the xy plane. And here you're seeing that the x lies between 3 and 4, right? If you come over here and you extend out, the x is going between 3 and 4, and the y is between 1 and 2 over here, right? So this is a region, a rectangular region, where the x is between 3 and 4, and the y is between 1 and 2. Right, so I have a rectangular region, and if I have a rectangular region, I want to do a double integral over a rectangular region, right? How you do it is you can integrate with respect to y first, and then with respect to x, right? Okay, so how you want to read this is, anyway, so all of these, when you're doing your double integrals, you're going to be working from the inside out, right? So you evaluate your inside integral here first. This inside integral over here, this is an example of using partial integration, which I talked about up here. Right? So you'd work out this inside integral over here, the one inside the bracket, first of all, using partial integration. And then the answer, what you're going to do is then integrate that with respect to x. And when you integrate that with respect to x, when you do your second integral, you're just going to get a value. Right? Now, in the case of a rectangular region, right? Okay, notice what I just said over here is I integrated with respect to y first and then with respect to x, right? In the case of a rectangular region, you can actually integrate with respect to x first and then with respect to y, right? You want to make sure that you keep track of your limits though, right? Here, when you're doing this integral here with respect to y, right? What you're doing is you need y limits, right? And the y limits come from the c and the d over here, right? Okay, so you have your y limit, lower y limit is c and upper y limit is d, right? And then this x over here, where you're integrating with respect to x, right? The limits corresponding to those are the b and the a, right? Okay, so when you integrate in respect to y first on this inside integral, if you integrate with respect to y over here, you'd want y limits, right? And when you're doing the outside integration here, where you're integrating with respect to x, what you'd need is x limits, and the x limits are a and b over here, right? Okay, so that's doing it this way, right? If you integrate in with respect to x first, right, and you can do it like this if it's a rectangular region. So if you integrate in with respect to x first, what you need is you need x limits here, right? And the x limits come from the a and the b here, right? And then you'd need y limits to do the outside integration, and the y limits would come from here, the c and the d here, right? Right. Okay, so let's see an example of evaluating this double integral over a rectangular region, right? Okay, so your function f of xy is x squared y, and your rectangular region, the x goes between 0 and 3, and the y goes between 1 and 2, right? Right. Okay, so I'm going to use Fubini's theorem, right? And what Fubini's theorem says is that I integrate with respect to one of the variables first and then integrate with respect to the next one, right? I'm making sure I use appropriate limits of integration. Okay, so here I have a choice. I can integrate with respect to y, then x, x, then y, right? And what you're going to see is, especially when you get to say like type 1 and type 2, right? It's more natural to integrate with respect to y first, and then x, right? Rather than do it this way, where you integrate with respect to x and then y, right? So it's usually preferable to do it this way, integrate with respect to y first and then with respect to x. It's if you want, it's less confusing, right? So I'll do it this way, right? I integrate with respect to y and then with respect to x. Okay, so I want to evaluate this double integral x squared y where I'm integrating over a rectangular region, right? Okay, so what you do is you set up, you're using Fubini's theorem, right? So to work out this double integral, you're going to do two integrals over here, first with respect to y and then with respect to x, right? Okay, so this over here is called a double integral, right? And once you do in this here, right, where you're integrating once and then you're integrating again, right? That actually is called an iterated. What you're doing here is an iterated integral, right? So you're doing iterations, and here you have two iterations. First integral here, second integral over here, right? Would usually sometimes I'd abuse the notation and just refer to this iterated integral as just as a double integral, right? Anyway, so if I'm gonna be using my Fubini's, what I'm gonna do is the function which is the x squared y, I'm gonna integrate with respect to y first, and then with respect to x, right? So I put this in brackets over here to indicate that I'm gonna do this inside integral here first, right? And when you're integrating over here with respect to y, you want to make sure that you have your correct limits. So for when you integrate with respect to y, you want y values 1 and 2 here, right? So you want y values 1 and 2 here, right? And then for when you're integrating, once you work this out and then you integrate with respect to x, what you need is the x values over here, the 0 and 3, right? So once you have this and you set it up like this with the iterated integrals via Fubini's theorem, right? You want to make sure that your limits here are correct, right? So the 1 and 2 for this y over here, so the y values, the limits of the y over here would be 1 and 2, right? And then the limits for the x would be the 0 and the 3, right? And now once you have this set up correctly, now you start doing the integration, right? This inside integral over here, you're going to do it via partial integration. So over here, what you do is you're going to be integrating with respect to y, right? The x squared is a constant. So when you integrate the y, you're going to get y squared on 2, right? The x squared just comes along as a constant. So what you get is when you integrate, you get x squared, y squared on 2, right? What you need to do is once you have this over here, you substitute your values. Y is equal to 1 and y is equal to 2. So that's what this means. You do your integral. And this notation means that in the next step, we're going to put in y is equal to 2 and y is equal to 1, right? Notice I still have to do the outside integral, right? So what I did over here is I'm working on the inside integral here first, right? I didn't start working on the outside integration as yet, right? So right now I'm still focusing on the inside integral. Anyway, so integrate the x squared y with respect to y, I get x squared y squared on 2. And now I put in my y values, y is equal to 2 and y is equal to 1, right? Put in y is equal to 2, I'm going to get 4x squared on 2, or 2 squared x squared on 2. And put in y is equal to 1 gives me x squared, well, 1 squared times x squared on 2, which is just x squared on 2, right? So this is 4x squared on 2, this is x squared on 2. Now again, all I'm doing over here is just working out the inside integral here first, right? I didn't start working on the outside. And here, what I have is 4x squared on 2 and then x squared on 2, right? When I subtract, I get 3x squared on 2, right? I notice after I finish working out this inside integral just works out to be 3x squared on 2, right? And once I have this, now this is just now normal integration, right? So the y went away in this first inside integral, right? You end up with 3x squared on 2, and this is just normal integration now, right? And you do your normal integration, so you're going to get x cubed over here, and you divide by 3. The 3 over here will cancel with this 3, so you got x cubed on 2. And then you put in the 3 and the 0, right? When you put in the 3, you're going to get 27 on 2. When you put in the 0, you're going to get 0 on 2. And when you subtract them, you're going to get 27 on 2, which is your answer. Okay, so let's take a look at our next example of doing a double integral over a rectangular region, right? So we look at this example here. Right, so I'm given a function of two variables, right? F of xy is equal to xy plus e to the y, right? And the graph of it is this purple shaded surface here, right? And what they're asking you to do is they're asking you to find the volume under the graph of this function, right? That's above your region R here, right? And they're telling you that your region R is a rectangular with corners 3, 1, right? So one corner over here is 3, 1, and the next corner over here is 4, 2, right? So the x over here is 4, and then the y over here is 2, right? Okay, so corner 3, 1, and 4, 2, right? Okay, and they want you to get this volume by working out a double integral, right? Okay, so they're asking you to use Fubini's theorem to evaluate this volume by working out this double integral over here, right? Okay, and your region R, of course, is a rectangular region. That's given as a rectangular region, right? So what we're trying to get is trying to get this volume over here, right? And notice this is your region R down here. You're taking your region R and you're projecting it up until it hits the graph of your function, right? And what I want to get is I want to get the volume of this this three-dimensional object over here, right? Okay, so I'm going to use Fubini's theorem, right? And Fubini's theorem, I can integrate with respect to y first and then with respect to x, right? So my function is xy plus e to the y, right? I integrate in with respect to y. So what you need is y limits, the 2 and the 1, right? And then you need the x limits, 3 and 4, right? Okay, so the fact that the y, you integrate in with respect to y first means that you want to put the y limits on the inside here first, right? Because you're just doing this first of all, right? Notice this is from a calculus textbook. I notice they didn't put a bracket to indicate that you're going to be doing the integral with respect to y first. It's understood that when you're doing this, you're going to do the inside integral here first, right? So what do I mean by that? Right, in the example that we just did, right, I put a bracket over here, right, to indicate that you're going to be doing your inside integral here first, right? So you have this big bracket here and here, right? But when you're doing these in standard, say like textbooks and so, they don't use these brackets like this over here. It's understood that you're going to be doing the inside integral here first. Right, okay, so I'm doing my inside integral here first. The y limits are 1 and 2, right? So 1 and 2, and then for the x, the limits are 3 and 4, right? Right, so you're doing the inside over here and you're integrating partially with respect to y, right? So when you integrate this xy with respect to y, the x is a constant, so you'll get the y squared on 2. So integrating the xy gives me a half xy squared on a half xy squared, right? When I integrate y with respect to y, right, it's an exponential. You're just going to get the e to the y, right? Okay, so you should know that this is just a standard way of integrating exponentials, right? If you integrate e to the x with respect to x, you just get back to e to the x, right? So likewise, if I'm integrating e to the y with respect to y, I just get back to e to the y, right? And here, what I need to do is I need to evaluate at y is equal to 1 and y is equal to 2, right? So the notation here is extremely good, right? Because it's not sort of clear what you substitute in here, right? I mean, they have the 1 and 2 over here, and I suppose it's understood that what you're doing is you're putting in y is equal to 1 and y is equal to 2 over here, right? So again, compared to what I did in my notes, right? When I did this first integral and I worked it out, right? What I'm doing it is putting in y is equal to 1 and y is equal to 2. So I'm specifying here that it's y is equal to 1 and y is equal to 2 that I'm putting in, right? But anyway, it's understood here that you put in y is equal to 1 and y is equal to 2, right? Now, they put in y is equal to 2, they put in y is equal to 1. What they did is they just worked it out one time, right? So what I'll do for you is I'll just do the intermediate step here. Right, so here, this is, you get this is after you integrate partially with respect to y, and you put in the y is equal to 1 and y is equal to 2, right? When you put in the y is equal to 2, you're going to get 2 squared, which is 4, so you're going to get 4x on 2. And you put in y is equal to 2 into this, gives you e to the 2, right? And then also you put in the y is equal to 1 into this over here, which gives me 1 squared, so this is just a half x, which is just x on 2. And then the y is equal to 1, which is e to the 1, which is just e, right? So this over here is when I put in y is equal to 2. And this over here is when I put in y is equal to 1. And then what you do now is you need to subtract these. And when you subtract this, you get 4x on 2 minus x on 2, which is 3x on 2. And you can't really do anything about these. This e squared is just a constant, right? So e is about 2.71 or something like that, right? Okay, so when you square it, you'll get something that's roughly probably close to 7, right? So this value over here is about 7, and this is just your 2.7. So these are just constants over there, right? Okay, right, so you go from here to here, right? Okay, so as I said, you just had a step missing going from here to here, right? And I just explained how you work it out, right? And once you get to this point, what you want to realize is that now this is just a function in x alone, right? So once you do your first integral here with respect to y, right, the y is going to go away, right? And you're just going to be left with something just involving x, right? And now this is just normal integration, right? With respect to x, and you integrate the x over here, you're going to get x squared on 2. So the 2 will hit that 2 over there, will hit this 2 over here to give you a 4, right? And then this is just a constant over here, right? So if you integrate a constant with respect to x, you get the constant times x. And now they just simply put in x is equal to 4, x is equal to 3, and subtract, and you get this answer over here, right? And they work it out numerically for you. This is 9.92, right? Okay, so this over here, this 9.92 is just the volume of this three-dimensional object over here, right? It has 6 faces, your bottom face, that is R, 4 vertical faces here, and then this top face over here that is coming from the graph of your function. Right, okay, so that was integrating with respect to y and then with respect to x, right? What you could do is you could integrate with respect to x first and then with respect to y, because this region over here is rectangular, right? Notice you will not always be able to do this. If your region here is not rectangular, this sort of switch in the order of integration, you can't always do it, right? Or it's not that straightforward, right? Okay, in this case, it's relatively straightforward because the region here, this region is rectangular, right? Okay, so let's work it out where I integrate with respect to x first, then with respect to y, right? You want to notice that when I'm integrating here with respect to x first, the limits here now are the 3 and 4, right? Which are coming from the x interval over here, right? So the lower value here is 3. This is 3 over here. The upper value here is 4, which is this 4 over here, right? So I'm doing this inside integral here now with respect to x. So what I need here is x limits over here. Then once I work this out, I'll integrate with respect to y, and for that I'd need y limits, which are 1 and 2, right? Okay, so I'm integrating with respect to x now, and when I integrate the x, I'm going to get x squared on 2, right? Right, and then when I x squared on 2, and then the y will just come along as a constant, right? So I'm going to get a half x squared y, right? And again, what I'm doing here is I'm integrating with respect to x, right? And if I integrate e to the y with respect to x, I'm just going to get x e to the y, right? Because if I'm integrating with respect to x, this e to the y is just a constant, right? Okay, and if you integrate a constant with respect to x, you get a constant times x, right? So I get x e to the y over here. And now what I need to do is put in my x values, which are 4 and 3, right? Right, and again, he skipped a step over here, right? What you need to do is put it in for 4, put x is equal to 4 into this, put x is equal to 3 into this, and subtract, right? I'll just explain how it is you got these values. So when you put in the 4, you're going to get you'll get 16 over here, right? 16 on 2, right? So you get 16y on 2, right? When you put in the 3, you're going to get 9y on 2, and you're going to subtract, right? So what you'll have is 16 on 2 minus 9 on 2, which will give you the 7 on 2 over here, right? Okay, and then likewise for this term, you put in the x is equal to 4, you'd have 4 e to the y. When you put in the x is equal to 3, you have 3 e to the y. So you're going to be subtracting 4 e to the y. You're going to subtract in 3 e to the y from 4 e to the y, which leaves you e to the y over here, right? So that's how you'd work it out, right? And then now this over here is just normal integration with respect to y, right? You integrate the y, you're going to get y squared on 2, so that's why you get this 4 down here. Integrating e to the y with respect to y just gives you the same thing, and then you just put in your values 1 on 2. And the answer that you're going to get would be 9.92, which is the same as this over here, right? Well, notice this form over here with the exponentials is exactly the same as this, right? Okay, so that is justifying, that's an example of Fubini's, right? For that example, what I did is I integrated with respect to y first, then x, right? And then I integrated with respect to x, then y, right? And in both cases, I get the same answer, right? So that is what this is saying over here, right? If you integrate in over a rectangular region, you could integrate with respect to y first, then x, or x, then y. Either way, you get the same answer, right? And usually if you're doing this and you just want to work out the answer, you'll just do one way, right? You don't need to do both ways, right? Unless the question asks you specifically to check to see if you're gonna if you do it this way, you're gonna get same answers if you do it this way. Okay, all right. So let's look at what these type 1 and type 2 regions are, right? Right. So what a type 1 region is you want to realize that this is in a sense has a sort of rough rectangular shape, right? What you have is, and this is in the xy plane, right? So this is a region in the xy plane. You have two vertical lines over here, right? But instead of, in the case of rectangular, where you'd have two horizontal lines, the top and the bottom here could now potentially be curves, right? And how you describe these curves, you describe them by y is equal to f of x, right? So you have y equal to f of x describing your top curve over here, and y is equal to g of x describing your bottom curve over here, right? Okay, so a region that is enclosed by two vertical lines, x is equal to a and x is equal to b. In other words, the x lies between a and b, right? So here you see that the x is lying between a and b. and y values lie between two curves. Y is equal to f of x and y is equal to g of x. So the y values align between f of x and g of x. Now, unfortunately, there's a mistake here, right? Because this should be inverted, right? The f of x should be over here and the g of x should be on top. Right, okay, so between, for a type 1, right, you're going to be between two vertical lines here, x is equal to a and x is equal to b, and two curves over here, g of x and f of x here, right? For type 2, it's a similar sort of rectangular shape, right? But for type 2 now, what you have is the region is between two horizontal lines, uh, y is equal to c and y is equal to d, right? So this is your line y is equal to c over here, and this is your line y is equal to d, right? And you see that your y values lie between c and d, right? So that is what this is saying over here. The y values align between c and d, right? And the x values align between two functions of y, right? So x of x equal to h of y over here and x is equal to k of y over here. The x values align between those, right? Okay, so what we're looking at is points where the y values lie between c and d, right, like this, and then the x values lie between two functions of y. Alright, okay, so as an example, let's consider this triangular region here, right? So this triangular region is a region in the xy plane, right? And I want to express this as, well, first of all, you want to realize it's not a rectangular region, right? Okay, and I want to express it as a type 1 region, and it turns out that this I can also express as a type 2 region, right? So let's do the type 1 region, right? Okay, so let's probably... Okay, so I want to express it as a type 1 region first of all, right? So what is it? What does it mean for it to be a type 1 region, right? Well, it means that the points have to lie between two x values, right? X is equal to a and x is equal to b, right? Now, if you notice this triangular region here, it lies between x is equal to 0 and x is equal to 4, right? So as a type 1, right, these values here would be 0 and 4, right? Okay, and then the y values have to lie between two curves, right? Notice the y values here lie between two curves, y is equal to f of x and y is equal to g of x. So likewise, the points inside here need to lie between two curves, right? Y is equal to g of x and y is equal to f of x, right? So, well, what's the top curve over here, right? The top curve is this y is equal to f of x, and this function over here, this is a straight line, right? So I can get y in terms of x just from the equation of this line over here, right? You notice that, well, okay, your intercept over here is 2, right? And if you notice here, the slope would be negative, right? And you can always work out the slope and see that the slope is minus a half, right? Okay, so the equation of this straight line over here is y is equal to 2 minus x on 2, right? Okay, so what's happening here is that your points align between two curves. One is y is equal to 0 over here, which is this x-axis, right? And then the top curve over here, which is y is equal to 2 minus x on 2, right? Okay, so the answer would be, I'd have 0 and 4 over here, which is the 0 and 4 coming from these points lying between x values 0 and 4. And then the y values lie between two curves, the curves y is equal to 0, and then the curves y is equal to 2x minus 2, right? And that's actually the answer that they have here, right? When they work it out, right, notice they get the x line between 0 and 4, and the y lying between 0 and 2 minus x on 2, right? So in this case, the a is equal to 0, the b is equal to 4, the f of x is 0, and then the g of x is 2 minus x on 2, right? Right, and it turns out that this same region here can also be expressed in terms of type 2, right? So when you describe the set of points in this blue region here, it will take this form, right? You can write it in set notation this way, right? Okay, so, well, what you need, right? What you need is you need to, for these points, you need y values, right? Such that the points inside here lie between, say, a y. It needs to lie between two horizontal lines, right? Y is equal to c and y is equal to d, right? And if you look at these points over here, they are lying between two horizontal lines. They're lying between y is equal to 0 over here, which is the x-axis, and they're actually lying below y is equal to 2, right? Okay, so the c and the d over here would be 0 here and 2 over here, right? And well, once you have that, what you now need is you need two functions, x in terms of y, right? Okay, so this y is equal to 2 minus x on 2, right? What you can do is you can express this x in terms of y, right? You just solve for x over here. And when you do that, I get 2y over here, I get a 4 over here, right? Okay, and solving for the x in terms of y would give me x is equal to 4 minus 2y, right? Okay, so the equation of this line over here, x in terms of y, would be x is equal to 4 minus 2y, right? And they in fact worked it out over here, right? Right, so the equation of the line, which is y is equal to 2 minus x on 2, right? You can also write it as x is equal to 4 minus 2y. Anyway, so what I have is for this region here, if I want to express it in terms of if I want to express it as a type 2 region, right? I'd need the c and the d, right? And the c over here would be 0, and the d over here would be 2, right? You're lying between two horizontal lines, y is equal to 0 and y is equal to 2, right? So the c is equal to 0, the d is equal to 2, right? And then the points in this blue region are lying between two curves, x in terms of y, right? So this y-axis over here is x is equal to 0, and this curve over here is x is equal to 4 minus 2y, right? So what we expect is we'd expect when this region expressed as a type 2 region, what you'd have is the y line between 0 and 2, right? So the y line between 0 and 2, and then the x would lie between x is equal to 0, which is a y-axis, so you'd have a 0 over here, and then the x, the upper bound over here, right, the top curve over here would be x in terms of y here, which is x is equal to 4 minus 2y, right? So you'd have 4 minus 2y over here, right? Okay, so this would be, the c would be 0, the d would be 2, right? This k of y over here, right, which is corresponding to this, right, which in this case is x is equal to 0, right? So this function is 0 over here. And then finally, this top function here, right, x is equal to h of y is what you get by expressing x in terms of y over here, which is x is equal to 4 minus 2y, right? So the answer would be 0 here, 4 minus 2y, right? 0 here, and 2, right? And that's the answer that they have over here, right? Okay. The y is lying between 0 and 2 here, right? And then the x is between 0 and 4 minus 2y. Okay, so let's take a look at some examples or some illustrations of type 1 and type 2 regions. Right, so this is from book Open. This is Calculus Volume 3 from OpenStax. Here they have a definition of type 1, and this is the same as my definition, right? A little slightly different notation. They use g1 of x and g2 of x over here, right? So g1 of x is the bottom curve and g2 of x is the top curve, right? Okay, so a region in the xy plane is type 1 if it is lying between two vertical lines, x is equal to a and x is equal to b, right? So notice this region here is lying between x is equal to a and x is equal to b. And the points in your region lie between two curves of the form y is equal to g1 of x and y is equal to g2 of x, right? So any point over here satisfies the x line between a and b, which means that it lies between these two vertical lines. And the y lies between g1 of x and g2 of x, so it lies between these two curves, right? Two graphs of functions g1 and g2 of x. Okay, so a next example of type 1 is, say, this one over here, right? Notice again, the x values lie between two vertical lines, x is equal to a and x is equal to b. And your points over here, they lie between the curves y is equal to g1 of x and y is equal to g2 of x, right? So it satisfies x line between a and b. In other words, it lies between these two vertical lines. And y line between g1 of x and g2 of x. So it's lying between these two graphs of functions. Okay, so this one is also type 1. You could look at this here and convince yourself that this is also type 1. Now, for type 2, a region is type 2 if it is lying between two horizontal lines, y is equal to c and y is equal to d, as this region is d over here, right? And then the x values lie between two functions of the form x is equal to h2 of y and x is equal to h1 of y, right? So this here is this one is a type 2 region, right? And similarly, this one is a type 2 region. The region lies between two horizontal lines, y is equal to c and y is equal to d. And the x values lie between two functions of y, as this one does, right? Okay, so this here satisfies, or this here, the region D, can be expressed in this form here. Right, so let's take a look at an example of evaluating a double integral when the region D is a type 1 region, right? Okay, so I want to integrate, I want to calculate a double integral of this function of two variables when the region in the xy plane is this y is equal to half x. But the region in the xy plane is specified by this triangular region. Okay, so we want to write this here we want to express as a type 1 region, right? First thing you want to notice is, well, we have this is a triangle, it's a right angle triangle, and we know what the vertices are, right? The vertices are the origin 0, 0, this point over here 2, 1, and this point over here where x is equal to 0 and y is equal to 1, right? Right, if I want to express this as type 1, right, if it's going to be type 1, it would have to be, you need to have a top curve and you need to have a bottom curve, right? And the top curve and the bottom curve would be in terms of x, right? So you want y is equal to a function of x on the top and y is equal to a function of x on the bottom. Okay, so this here, the top is this horizontal line and the bottom is this this line with positive slope, right? Alright, so your top is y is equal to 1 and the bottom is y is equal to half x, right? So the y is going to lie between the top curve, which is 1, and the bottom curve, which is a half x, right? and then the x values lie between 0 and 2, right? Okay, so how do we evaluate a double integral over a type 1 region? And how you evaluating double integral over a type 1 region is you using this formula over here, right? So this is similar to the Fubinis that we saw a little earlier, right? Okay, so to evaluate a double integral, you're going to integrate with respect to y first, then with respect to x, right? It's similar to the case of when r is rectangular, right? So if you integrate in with respect to y, what you need is y values here, right? And now the y values are not going to be constants, right? The y values are in fact going to be functions of x. Okay, so remember your y values from here to here, right? The limits, right, of integration are going to change according to what the x is, right? So these are not no longer constant values for y, right? These your functions of x, right? Okay, so if you gonna do a double integral over a type 1 region, what you're going to do is, and this is the type 1 region specified for you, when you do any inside integral here first with respect to y, your y limits of integration would be, this would be a top y limit f of x, and this would be a bottom y limit g of x over here, right? Okay, and then you would do this inside integral, and then once you work this out, you integrate your result with respect to x, right? So your outside integration, where you integrate with respect to x, the limits would be a and b, right? So these are x limits, right? X limits of integration, and that's actually from the a and the b over here, right? Okay, so if it is type 1, what you're going to do for type 1 is you always integrate with respect to y first, and then you integrate with respect to x, right? So you evaluate this here with respect to y, you integrate here partially with respect to y, you get your answer over here. This, when you work it out, will be a function of x alone, right? And then once you get that, you're going to integrate this function of x with respect to x for your limits a and b, right? So that's how you would work out a double integral over a type 1 region, right? So let's go back to our example. Okay, so we want to evaluate this double integral here for this over this type 1 region here, right? Right, so your top curve is y is equal to 1, so that's this 1 over here. The bottom curve is a half x here, and you go in between vertical lines, x is equal to 0 over here, and x is equal to 2 over here, right? So that's what you have, right? And it being a type 1 means that you need to integrate with respect to y first, right? So the inside integral is with respect to y. And when you integrate in with respect to y, you need y limits of integration, right? Your bottom limit is a half x, which goes over here, and the top limit is 1 over here, right? So first you're going to work out this inside integral here first, right? Okay, so we're working out our inside integral here first, right? This is an iterated integral, right? And we integrate with respect to y first, right? So when we integrate with respect to y, well, the x squared is a constant, right? So it'll just come along. You're going to integrate the e to the xy, right? Now, this is integrating basically exponential e to the y, where you just have a coefficient in front of this y over here, right? So the x is a constant for you, right? Right, so when you integrate something like this, what you're going to do is, so when you integrate an exponential for a variable which is a constant over there, remember you're just going to divide by the constant, right? Okay, so your constant over here is x, and you divide by that x here, right? Right, okay, so the integral of this here with respect to y is x squared e to the xy on x, right? And this x will cancel with this x over here, right? Anyway, so once you have that, what you do is you put in your values, y is equal to 1 and y is equal to half x, right? When I put y is equal to 1 into this, I'm going to get e to the x over here, And as I said, the x will cancel with the x squared, so I get x e to the x, right? And then you put in the y is equal to half x, right? And when you put in y is equal to half x, you're going to get e to the x squared on 2, right, inside here, right? And then you're going to get the x. This x will cancel with this x squared, so you get the x over here, right? Right, okay, so what I have is this expression over here, and now what I need to do is I need to integrate this with respect to x, right? This is just integration with respect to x, and you should know how to do this, right? But this one here, what you want to do is you're going to use two different techniques, right? This first one here, the x e to the x, you need to integrate that by parts, right? And when you integrate that by parts, you're going to get x e to the x minus e to the x, right? So integrating this first piece over here, you will integrate that by parts to get the x e to the x minus e to the x. And this second piece over here, right, in order to integrate this, you'd need to use the substitution u is equal to half x, right? So the substitution really is more of this second part over here, right? And when you use that substitution, you're going to get the integral of the x e to the x squared on 2 is e to the x squared on 2, right? Okay, and then once you have that, you just substitute x is equal to 0 and x is equal to 2, and this will work out to be equal to 2, right? Right, okay, so let's look at this example from the notes, right? I have this double integral, and I want to integrate over a region R in the xy plane. They didn't tell you what type of region it is, right? And they didn't, so they just tell you that the region is bounded by lines x is equal to y plus 1 and a parabola x is equal to y squared on 2 minus 3, right? Okay, so you want to graph both of these, right? So x is equal to y plus 1. Well, this is just a straight line, right? Where your slope is, if you carry this 1 across on this side, what you'll get is y is equal to x minus 1. Okay, so that tells you that this is going to be a straight line with intercept over here of minus 1, right? Okay, so your y-intercept over here is minus 1. Your parabola, on the other hand, this is equal to x y squared on 2 minus 3, right? So if you forget about the minus 3 for the time being, right? A parabola x is equal to y squared on 2 will face this way over here, right? Okay, so remember your parabolas, say like y is equal to x squared, will open out in this direction over here, right? So this is y is equal to x squared will look like this, right? Right, so let me remind you about graphing your parabolas and so, right? Okay, so this is y is equal to x squared, right? And y is equal to x squared, you know it's a parabola passing through the origin, right? Now, in the question for the double integrals that I'm looking at, right, what I have is not y is equal to x squared, but something along the lines of x is equal to y squared, right? Well, it's y squared on 2, right, minus 3. But for the time being, let's consider x is equal to y squared, right? Right, so this is your graph x is equal to y squared, right? The blue one over here is your graph x is equal to y squared. And the green one is y is equal to x squared, right? Okay, so what you want to notice between these two, right, is you exchange the roles of x and y, right? And when you exchange the roles of x and y, what you're doing is you actually reflect in your graph. You reflect in the line y is equal to x, right? So if I have the graph of y is equal to x squared, which is this green one, and I want to get the graph of x is equal to y squared, right? What I will do is and if I want to get a graph of x is equal to y squared, right? Well, what you're doing is you can exchange the roles of the y and the x, right? And you would have seen that when you were back in your form 4 and form 5 maths when you were getting the inverse of a function, right? Okay, so if you want to exchange the roles of the y and the x, what you do is you can reflect in this red line, which is y is equal to x, and this red graph would be what you would get when you reflect this green curve over here in the line y is equal to x. What it will do is, instead of opening out in this y direction, your curve x is equal to y squared will now open out in this x direction over here, right? Okay, and well, what is it that I have, right? What I in fact have is the parabola is x is equal to y squared on 2 minus 3, right? So if this is y squared on 2, right, the y squared on 2 will just change the shape of the graph, right? It'll widen it slightly. And what I actually have is x is equal to y squared on 2 minus 3, right? So the minus 3 now will just shift it back. Okay, it'll shift it to the left by 3 units. Right. So this would be what your parabola x is equal to y squared on 2 minus 3 would look like, right? And that is what I have in my notes, right? This is x is equal to y squared on 2 minus 3, right? Okay, so what I want is, when I'm working out this double integral, I want to get a region bounded by this straight line x is equal to y plus 1, right? And your parabola x is equal to y squared on 2 minus 3, right? Which is this parabola, right? So the region bounded over here is this dark gray region over here, right? Okay, and this region, well, it's certainly not a rectangular region, right? And this here, it's not easy to express this as type 1, right? In order for you to express this as type 1, what you'd have to do is you need to actually cut, right? You need to cut this into 2 pieces, right? Because the problem is, while you could use this as your top curve over here, right? When you come down on this side, right? The bottom curve up to here would be this particular curve part of your parabola, right? But then at this point over here, your bottom curve now changes, right? And it changes to the straight line, right? So in order for you to express this as type 1, you'd need to actually cut this into 2 regions, right? Now that's a little difficult, so it's easier if we just express this as a type 2 region, right? And for a type 2 region, remember what's the form of a type 2 region, right? A type 2 region, the form of it is you have x is equal to a function of y and x is equal to a function of y, right? And in fact, you already have that, right? This line over here is x is equal to y plus 1. So the straight line over here is x is equal to y plus 1. So this is the top curve here. And the bottom curve, which is the parabola. Okay, so this is top over here and this is bottom over here, right? Remember, your x is increasing in this direction, right? So the x values over here would be larger than the x values over here. So this is top curve over here and this is bottom curve over here, right? Okay, so this was the x is equal to y plus 1 is your top curve, and the parabola x is equal to y squared on 2 minus 3 is your bottom curve over here, right? So if you're comparing it to your general picture, right, the top curve is this one, right? And the bottom curve is this one, right? Okay, so this is a region that is type 2, right? Now, if it's type 2, you have top curve in terms as a function of y, bottom curve as a function of y, and it needs to lie between, the region needs to lie between 2 horizontal lines, which this one does, right? It lies between your line y is equal to 4 over here, right? And then your line y is equal to minus 2 over here, right? Okay, so it's lying between 2 horizontal lines as what you expect from your general picture, right? Okay, so this is a type 2 region here, right? And well, how do we evaluate a double integral for a type 2 region, right? Well, how you evaluate it is given by this formula over here, right? Now remember, when it was type 1, right, what you were doing is you integrate with respect to y first, right? Now for type 2, what you do is you integrate with respect to x first, right? Now the x is lying between two functions of y, right? So your limits of integration for the x now would be these functions of y. This is the top one, the h of y. This is the bottom one, the k of y, right? And so this is this, you do the inside integral here with respect to x, and then the outs you will perform once you evaluate this, you're going to get a function in y alone, and then that you will integrate on the outside with respect to y. So when you integrate on the outside with respect to y, what you need are y limits of integration, and the y limits of integration are c and d, right? Okay, right. So in this case, we express this as a type 2 region. The top curve is x is equal to y plus 1. The bottom curve is x is equal to y squared on 2 minus 3. And then the y values lie between minus 2 and 4, right? Okay, and you're seeing that over here, right? The top curve is x is equal to y plus 1, which is this straight line here. The bottom curve is x is equal to y squared on 2 minus 3, which is this parabola here. Okay, and then the y value is a line between minus 2 over here, right? And then y is equal to 4 over here, right? Okay, so this is, you have your region over here, and now you express it as a type 2 region, right? And once you have this, now you can do your integration, right? Okay, so I want to evaluate this double integral of xy over this type 2 region, right? And as I just said, what you do is you integrate with respect to x first, right? Now when you integrate in with respect to x, what you need x limits, and the x limits, the top x limit is y plus 1. The bottom x limit is y squared on 2 minus 3, right? Okay, so I need to work out this inside integral here first. I'm integrating with respect to x. So I will get x squared on 2 over here, right? And the y will come along as a constant, right? Okay, and once I have that, I need to substitute my x limits of integration, which are y plus 1 and y squared on 2 minus 3, right? Okay, so I substitute y plus 1 into this, which gives me substitute y plus 1 in for x, right? So I'd have y plus 1 squared here, right? Times the y, right? Notice what I did is, for simplicity, I would this constant where I'm dividing by 2 or multiplying by a half, I can actually pull that outside. So I pull the half outside. So all I'm looking at over here is the x squared y. Anyway, so what I do is I substitute the y plus 1 in for the x over here. So I get y plus 1 squared here, right? And then likewise, I substitute x is equal to y squared on 2 minus 3 in for the x over here. So I'll need to square that and then again multiply by y, right? So I get something, an expression over here that involves y alone, right? Now, while it might look a little cumbersome, and so this really isn't too bad, right? Because all you have is just, this is just integral, normal integration in single variable, which is y over here, right? So in order to integrate this, what you just need to do is you need to expand this out. When you expand this out, you'll get this polynomial over here in y, right? You just need to go through the process of expanding it out. Here you get y squared plus 2y plus 1, right? And then you multiply each term there by y, which would give you the y cubed plus 2y squared plus y, right? And here you'd need to expand, you need to square this over here, so you'd get y squared on 4, right? And then you're going to get 3y squared, right? Because it'll be this times this, well, minus 3y squared. And then the minus 3 squared would give you 9, right? And then you multiply everything by y to give you this expression. And here what you do is you collect everything, right? You collect the powers. So what you can do is you can in fact group the y cubed together, so you'd get 4y cubed. You can group the y together, where you're going to get minus 8y. And you just integrate this with respect to y. You'd use power rule on each of these, right? And then the answer would be 36 here. So far what we looked at was double integrals over a rectangular region. So we looked at double integrals over a rectangular region such as this, right? So this is your three-dimensional picture, right? Okay. This R over here, your region R is down here in the XY plane, right? As I said, this is a three-dimensional picture. Okay, and we looked at examples of integrating where your region R was type 1 and type 2, right? Okay, so now what we want to look at is we want to look at double integrals where your region of integration is now going to be something called a polar rectangle, right? So your region here would be expressed in terms of polar coordinates, right? R and theta. So what I'll do is I'll do a quick review of polar coordinates. Right, okay, so a point in two-dimensional space in the plane could be specified by xy coordinates, right? So if you want to locate the point with given xy coordinates, what you do is you move along x-axis by x over here, and then you go up by y, right? And then this would locate your point xy, right? On the other hand, what you could do is you could specify your point, the location of your point using polar coordinates, right? So what you would do is you would okay, so the r and the theta here, the theta is angle measured counterclockwise from your x-axis, and the r is the distance of the point that you're interested in from the origin, right? Okay. Right, so to locate a point r theta given in polar coordinates, right, what you could do is with the angle theta here, right, you construct a line uh, passing through the origin at angle theta to the x-axis, where your angle here is measured in counterclockwise direction. And then as you go along this line over here, you want to go distance r, right, along this line, so that your point over here is going to be a distance r from the origin. Okay, so let's see an example of this, right? Let's look at this point over here, which is in polar coordinates, right? This is your point is 2 pi on 6, right? Okay, so the r over here is 2 and the angle is pi on 6, right? Okay, so if you want to locate your point 2 pi on 6 in the xy plane, right? What you could do is, well, you measure an angle pi on 6 from your x-axis, and you construct a line that is such that the angle between this line over here and this x-axis is pi on 6, right? And then you move along this line for a distance of 2, right? Okay, and this point over here, this would be a point 2 pi on 6, where the r is equal to 2 and the theta is equal to pi on 6. Okay, so you use your polar coordinates to locate a point on the xy plane, right? Right, okay, so this point over here, it has, you can express it in terms, well, you can get the coordinates as xy, or you can get the coordinates as r theta, right? And what you can do is you can use this diagram over here, right, to give you a conversion between xy and r theta, right? And you would have seen all of this before. As I said, this is review, right? Okay, so what you'd see over here from using, say, this right angle triangle, well, if you use this right angle triangle, you'd see that the length of this side is equal to r sine theta, right? Okay, so you get that y is equal to r sine theta. The length of this side is r sine theta. And the length of this side over here, which is the same as this x here, right? The x is equal to r cos theta, right? Okay, so this is of importance to us, right? Because when we're doing our double integrals, right? The double integrals would usually be specified in terms of x and y, right? And what we would need to do is we'd need to convert from xy to r theta, right? We'd want to convert, well, if the question requires a conversion to polar coordinates, this would be how you do it, right? You'd have x is equal to r cos theta and y is equal to r sin theta, right? Okay, so one thing you want to notice, right? If you consider x squared plus y squared, right, then that's r cos theta squared, and the y squared gives you r sin theta squared. When you square that, you get r squared cos squared plus r squared sin squared. You could pull out the r squared, and here I'm left with cos squared plus sin squared, right, which is equal to 1. The key thing you want to get out of this is that the x squared plus y squared is equal to r squared, right? Okay, so this also is useful for us when we're doing conversions from xy to polar, right? X squared plus y squared is equal to r squared. Okay, and if the r squared is equal to x squared plus y squared, you could take the square root of the r squared to get you the r, which means I need to take the square root of this x squared plus y squared. So I get this here, that the r is equal to the square root of x squared plus y squared, right? Alright, okay, and we'll need to sketch a couple curves or lines in polar coordinates, right? Right, so your first one over here is theta is equal to a constant here, right? Okay, now theta is equal to constant. What that does for you is that gives you actually a line that's passing through the origin at angle equal to this constant over here, which is labeled as beta here, right? Okay, so let's just see an example of that, right? I have theta is equal to a constant, and that constant is 3 pi on 4, right? Okay, and you want to remember that 3 pi on 4 is 90 plus 45, which is 135 degrees, right? Okay, so theta is equal to 3 pi on 4 is this red line over here, right? Okay, and you want to notice that your angle over here from your x-axis, measured from your x-axis as you go around over here, would be 3 pi on 4 radians, right? Which would be 135 degrees, right? Okay, so theta is equal to a constant value over here, right? Is simply a line passing through the origin where your angle measured from your x-axis is equal to this constant here, right? Okay, the next line or curve that we want to look at in polar coordinates is r is equal to a, right? And what r is equal to is, r is a circle of radius a centered at the origin. Okay, so for example, r is equal to 7 over here is circle, this red circle. We could probably ignore these. We wouldn't use these in this class, right? So we have r is equal to 7, which is a circle of radius 7 that's centered at the origin, right? So this red circle is a circle of radius 7 centered at the origin. And in polar coordinates, the equation would be r is equal to 7, right? Okay, so now what we want to do is we want to talk about the type of region that we're going to integrate over, right? Alright, so the type of region that we're going to integrate over in the case of for polar coordinates, right, would be something called a polar rectangle, right? So it's specified in the xy plane, right? But what you're doing is you're using r and theta now, right? Okay, so let's see if we could understand first of all what this r line between a and b means, right? Okay, so r less than equal to 5, what we could do is use that the r is equal to square root of x squared plus y squared, so replace that there. And once I have this, I square both sides, right? Okay, and if I square both sides, what I will get is x squared plus y squared is less than equal to 25, right? Right, okay, so what is that? X squared plus y squared less than equal to 25 is a circle of radius 5. Okay, it's a circle of radius 5. Right, and it's not just a circle of radius 5, it's a circle of radius 5 and then the interior of that circle of radius 5, right? So it's a disk over here of radius 5, right? So that's what x squared plus y squared less than equal to 25 is, right? Okay, so what that means for us is that this r less than equal to 5 is in fact a disk uh, of radius 5, right? So the disk of radius 5, the outer radius over here is 5, right? And by disk I mean the circle and everything in between, right? So that's r is less than equal to 5. Okay, so r bigger than equal to 3, what that will be is that will actually be a disk of radius 3, right? Okay, now that what I have over here is r less than equal to 3, right? This is r bigger than equal to 3, right? So r bigger than equal to 3 is actually everything outside of okay, it's everything outside of this disk of radius 3, right? Okay, so well, what do I have over here, right? What I have is, if I want to use this example, let's say I have r over here, all right, and I have 3 and 5, right? What would it mean, right? It would mean everything inside your circle of radius 5, but outside your circle of radius 3, right? Okay, so what would that look like? Right, so that is what it will look like here, right? R is equal, what you have over here is you have a circle of radius 3 and you have a circle of radius 5, right? Right, R is equal to 3 is the circle of radius 3, and R being bigger than, if I have R being bigger than 3 over here, it means that I'm looking at points outside of my circle of radius 3, right? And if this B was 5 over here, what I'd have is uh, looking at points inside the circle of radius 5, right? So this over here, this uh, R line between A and B, this is an example of R line between A and B over here, right? In this case, the A is equal to 3 and the B is equal to 5, right? So this expression, A R line between A and B, right, is in fact, well, a ring or annulus of annulus with inside radius over here and then outside radius, right? Your inside radius is this A over here, and then the outside radius is the B over here, right? Okay, so that is what this one is here, right? Right, and then what I'm going to have is uh, you have theta, you also have this inequality over here, right? Theta less than or equal to theta 2, right? And theta bigger than equal to theta 1, right? So what you want to do to get an idea of what this is you want to graph your lines theta is equal to theta 1. Right, so you want to graph your lines theta is equal to theta 1, and we talked about this. Theta is equal to theta 1 is a line passing through the origin where this angle here is theta 1, right? And theta is equal to theta 2 is a line passing through the origin where this angle here is theta 2, right? Okay, so what we're looking at is if we just focus on this, these inequalities over here, right? So the theta 1, the theta bigger than equal to theta 1 and the theta less than equal to theta 2, if we just focus on this one here, right? What that means is we're looking at points inside this wedge over here formed by two lines, right? Formed by the lines theta is equal to theta 1 and theta is equal to theta 2, right? So if you in a point over here, the theta value, say for this point over there, right, is bigger than theta 1. Okay, so a point like this over here, the theta value is bigger than theta 1, but it's less than theta 2, right? Okay, so this here means that you're actually in a wedge between your lines theta is equal to theta 1 and theta is equal to theta 2, right? And when you combine your inequalities with theta and your inequalities with r, right? Remember your inequality with r over here is your inequality with r over here. This r line between a and b is in fact an annulus, right? Okay, so your inside radius here is a and your outside radius here is b, right? Alright, so this graphic illustrates what's going on here, right? So your inequality here, r line between a and b, right? This is giving you an annulus, right? So the annulus would be this over here, right? Where you have inside radius a and an outside radius b, right? So that is what this one is doing for you, right? This over here, what this one with theta being bigger than equal to theta 1 and less than equal to theta 2, right? What that is giving you is that's giving you a wedge, right? So it's giving you a wedge like this, right? And in this case, this angle here, that angle is actually 45 degrees, and this angle going from, for this line over here, from here to here, that's 60 degrees, right? Okay, so it's 45 and 60, right? And I really should be using radians over here, so it's pi on 4 and it's pi on 3, right? Okay, so but anyway, these inequalities here involving theta, what it's giving you is it's giving you a wedge like this here, right? And what you want is when you combine the inequalities with theta with the inequalities with r, right? What that will do is that will cut out piece of your annulus, right? So that's actually okay. So this is your annulus over here, right? Which is coming from the a less than equal to r, which is less than equal to b, right? And you have your wedge over here, which is coming from the theta 1 less than equal to theta less than equal to theta 2, which is this sort of orange wedge here, right? But what we want is when we combine these, we're looking at the intersection of the areas. So that's actually this here, right? So your intersection of the areas is this, right? And this is the type of region that we want to integrate over, right? We want to integrate over polar rectangles that look like this, right? Now, this sort of polar rectangle, I drew an example of this, right? But what for different values of theta 1 and theta 2 and a and b, right? You'll get different types of shapes like this, right? I mean, they would all have this sort of general form as a polar rectangle, right? Okay, so for example, what I mean by that, right? If I use the inside radius here, right? Instead of okay, so this inside radius, instead of it being 3, right? Here this x squared plus y squared is equal to 9, so that's actually radius squared, right? Instead of using say 3 over here, if I use 0, what I would get is I would get this, right? In which case, if it's 0 over here, it means that your inside circle is basically circle of infinitely small radius, or just 0 radius over here, right? If you really wanted to get an idea. Right, okay, so this is when I have a small radius here, right? Small radius a, right? And that's this radius would be square root of 0.1, right? And if I reduce the radius down further, right, basically what I'll get is a circle of radius 0 over here, right? In which case I wouldn't be seeing the circle. Or in other words, all I'm getting is I'm just getting a disk of radius b, right? So this is when this a over here is equal to 0, right? Right, and in this case, your region is going to be, right, your polar rectangle. This is going to be a polar rectangle over here, right? Here, this is when the a is equal to 0 over here, and the b is equal to 3, right? If we want a next example of this, right, what we could do is we could change this. Okay, this theta is equal to theta 1, we could reduce this angle to 0, right? And if we reduce this angle to 0, this line over here will come straight down to your x-axis. Okay, so if we want a next example of a polar rectangle, right, where your angle here, this angle here is theta 1 is equal to 0. This angle here, theta 2 is equal to pi on 3, right, or 60 degrees, right? So this is 0 over here, this is 60 degrees, this is 0 over here, and this outside radius is 3, then that would be, right, okay, that would be this here, right? Okay, so your polar rectangle would be in this blue area in this case, right? So the point that I'm making over here is by having different values for the theta 1 and theta 2, right? The shape isn't necessarily going to look like this over here, right? It's going to look exactly like this, but in fact, it will fall into this sort of set description here, right? So I guess one more time, this set description here gives you a variety of possible polar rectangles, right? Or different shapes of polar rectangles, which may look somewhat different, right? But they're actually all described by this set notation here. Right, okay, so as an example of obtaining a polar rectangle, consider this region over here, which is specified in xy coordinates, right? Okay, so I have that the 9 x squared plus y squared lies between 9 and 25, right? Right. Okay, so x squared plus y squared is equal to 25 is a circle of radius 5, right? Okay, and x squared plus y squared less than equal to 25 would in fact give you a disk of radius 5, right? We saw this already, right? I'm just going over it again, right? Okay, so x squared plus y squared less than equal to 25 would give me a disk of radius 5, right? X squared plus y squared less than equal to 25 gives me a disk of radius 5, and when I consider x squared plus y squared lying between 9 and 25, right, what that gives me? That gives me an annulus where my radius, inside radius is 3 and the outside radius over here is 5, right? Alright, okay, and then I have, so that is this first part over here, right? And then I have x bigger than equal to 0, right? And x bigger than equal to 0, this gives me half a plane, right? Which is this half of a plane over here. Right, so this is where x is bigger than equal to 0, and y bigger than equal to 0 is this half of a plane over here, right? So when you combine the x equal to 0 and the y equal to 0, what you get in is you get in this first quadrant here, right? Right. Okay, okay, so your first quadrant would be, this is your first quadrant there, right? So that is when you combine x bigger than equal to 0 and y bigger than equal to 0, right? And what you want to do now is you want to combine these two inequalities, which is your first quadrant, with your annulus here, right? Okay, and when you combine them, right, the result that you would get would be part of your annulus, right? That lies between, that lies in the first quadrant, right? So your answer would be this annulus over here, but where it intersects this first quadrant, where the x is bigger than equal to 0 and the y is bigger than equal to 0, right? So your answer would in fact be this, right? This blue area over here, right? Okay, now, so if you want to express this as a polar rectangle, to do this, you'd first want to sketch the region, right? Okay, so this over here, really all that you're doing is you're really just using equations of circles, right? So for example, x squared plus y squared equal to 25 is a circle of radius 5. X squared plus y squared is equal to 9 is a circle of radius 3. And this sort of expression over here means that you're looking at an annulus where the inside circle is of radius 3 and the outside circle is of radius 5, right? Okay, so that is what this is doing for you, right? And this one over, these two over here is telling me that I'm in my first quadrant, right? This is half of a plane, this is half of a plane. And when I intersect the two half planes, I get the first quadrant here, which is this dark blue, dark purple area here, right? Okay, and then finally, it's you want to combine all of these, right? So this is your first quadrant intersected with your annulus, right? Which gives me my required polar rectangle, which is this piece here, right? Okay, but that is really just sketching the region, right? Now what we want to do is you want to express this as a polar rectangle, right? Now expressing it as a polar rectangle means I need to express it like this, right? Now if I'm expressing it like this part here with the R line be less the R between A and B means this over here is the annulus part if you want, right? So this would be your inside radius over here, and this is your outside radius over here, right? And in this case, your inside radius is 3 over here, and the outside radius here is 5, right? Okay, so the A is going to be equal to 0, and the B is going to be equal to 3, right? And now what we'd also want is the angles, right? So you have two lines, right? That form some sort of wedge. So this is a general picture, but over here, the two lines, one line would be a x-axis over here, and the next line would be a y-axis over here, right? And for x-axis, right, the angle there would be 0, right? So that is saying that the theta 1 would have to be 0 here, right? Okay, and then for the y-axis, the angle here would be the theta 2, right? And this theta 2, this angle is 90 degrees, but we want everything in terms of radians, so this is pi on 2, right? Okay, so the angle theta 2 is going to be pi on 2, right? Okay, so one more time, for your annulus, this is inside circle and this is outside circle, right? Your inside circle is of radius 3 here. Your outside circle is of radius 5, so you're going to get a 3 and a 5 here, right? These angles here, theta 1 and theta 2, are going to come from these lines, right? And the angle that these lines make with the x-axis, right? So this x-axis, this line over here is on the x-axis, so it makes 0 angle with the x-axis. So this is 0 here. And this y-axis over here makes 90 degrees or pi on 2 radians over here. So your theta 2 is equal to pi on 2, right? So that's how we're going to get the values here from a polar rectangle, right? So the answer here is that the r lies between 3 and 5, right? So the r lies between 3 and 5. And the theta lies between angle 0 here and angle pi on 2 here. Right, so we saw what a polar rectangle is, right? Now we want to integrate over the polar rectangle, right? So we want to integrate over a region R in the xy plane that say looks something like this over here, right? This is a polar rectangle, or it looks say something like this over here, which is a polar rectangle, right? Okay, so a polar rectangle, well, one way that you can identify, probably easily identify a polar rectangle is if you're looking at a region in the xy plane and the region somehow has an arc of a circle in it, right? You see in some sort of circle or something in your as a boundary of your region, well, then that suggests that you're going to have to do a conversion to polar coordinates, right? Which means that you're going to have to express your region somehow as a polar rectangle. Anyway, so if we want to integrate over something that is a polar rectangle, this would be the formula that allows us to do it, right? Okay, so this here is the form of a double integral, right? Right, so you have a function of two variables that we're going to integrate over a region R, right? And your region R, say, could look like this over here, right? Okay, so if I want to integrate over something that is a polar rectangle, right? Well, I'm going to do it by converting to polar coordinates, right? So this x over here, what you're going to do is where you see x in your function, you're going to replace the x by rcos theta, right? And that is coming from your conversion between polar and xy, right? So the x is equal to rcos theta, and so you're going to get this rcos theta over here. The y is equal to r sine theta, so you're going to replace the y by r sine theta to get this, right? And once you do that, you also you'll need limits of integration here, right? Okay, so before I get to the limits of integration, you replace, as I said, you replace the x by r cos theta, the y by r sine theta, and you're going to be integrating with respect to r and with respect to theta, right? In this particular case, you can actually, it doesn't make a difference what order you do it in, right? If you integrate with respect to theta, and then r, right, or r then theta, as I have over here, right? But usually when I'm doing these examples in class, and what you see in tutorial, is typical for us to integrate with respect to r first and then with respect to theta, right? But you can do any order that you want, right? Anyway, so here I'm integrating here with respect to r, and what I would need is limits for the r variable, right? And the limits for the r variable are coming from here, right? This is the lower limit a, and this is the upper limit b, right? So that's the a and the b over there, right? And then this outside integral is where I'm integrating with respect to theta, right? And I'd need theta limits here, right? And those come from, this is the lower limit for the theta, theta 1. Okay, so that's some constant angle. And then theta 2 over here would be the upper limit here, which again is some constant angle here, right? Okay, and then finally, when you're doing this conversion, right, you have this r showing up over here, right? Where that r comes from is that r, what you're doing here is you're changing coordinate systems from xy to r theta, right? And whenever you're doing that, there's something called a Jacobian of a coordinate transformation, right? And that's where that r comes from. We're not going to look at general changes in coordinates when it with respect to double integrals. So for us, we're just going to take this as when you doing your conversion to polar coordinates, you're going to have an r over here, right? Look at an actual question where we evaluating a double integral by using polar coordinates, right? Okay, so they give you your double integral, they give you a function over here, and they give you region r in the xy plane. And this r over here is specified as a set, right? So the first thing you'd want to do is you want to sketch this region, right? We talked about this, right? So this over here with the x squared plus y squared less than equal to 1, right? The outside circle here is a circle of radius 1, right? Okay. And then with this 0 over here, your inside circle is a circle of radius 0, right? In other words, it's just a point, right? It's just the origin there, right? So this over here, this is a disk of radius 1 over here, which is illustrated by this picture, right? Okay, and this disk of radius 1 we want to express as a polar rectangle, right? So we want to express using the sort of general form over here, right? And expressing it as a polar rectangle means that I'd want to determine what these values are, right? Okay, so this b over here is easy. This b is supposed to be the radius of the outside circle, and the radius of the outside circle you're seeing as 1 over here, right? So that's how I get this 1 here, right? The inside circle here, and this is sort of like a general picture. Your inside circle is of radius a, and here the inside circle is of radius 0, so I'm going to get a 0 over here, right? Theta is equal to theta 1 is the angle that your line over here makes with the x-axis. So theta 1 is this angle here, right? Well, what are the lines in this case over here, right? Well, the lines that you're going to have in this case here, right? In this case, right? Well, you could look at one line being your x-axis over here, right? Okay, so that line would be theta is equal to 0, right? Because the angle that the x-axis makes with itself is 0, right? Okay, so first line over here, theta is equal to theta 1 for this case here. The theta is equal to 0, which gives me this x-axis, right? What about the next line, right? Well, the next line, right? So let's see if we could get an idea what your next line is going to be, right? Okay, so by next line I mean, well, what's going to be this line over here, right? So I started here with theta is equal to 0, right? But what's going to be my second line here, right? Okay, so let's look at, say, this example here, right? Well, what would be this as a polar rectangle, right? Your radius here is 1, so the radius here is 1. Your inside circle here is 0 over here, right? Here you're starting at theta is equal to 0, right? So you're going to start at theta is equal to 0. But the angle in this case is equal to 3 pi on 2, right? Okay, right. So your second line, theta is equal Your second line, theta is equal to theta 2, right? Second line, theta is equal to theta 2. For this particular case, the theta 2 is going to be equal to 3 pi on 2, right? Right, so how does that help us here, right? Well, this is 3 pi on 2, right? And if I keep increasing this from 3 pi on 2, say say 7 pi on 4, which would be over here, right? And I keep increasing this, eventually what I will do is the this second angle over here, this one over here, this theta 2 over here, which is supposed to be over here, right? Okay, so in this case, right now it's 3 pi on 2, right? So this would be 3 pi on 2, right? If I increased it over here, right, then that would be 7 pi on 4, right? And if I keep increasing, what's going to happen is going to keep increasing until it actually comes back and it hits this 2 pi, right? Okay, so when you hit the 2 pi, right, what happens is that the second line actually falls back on the x-axis and you end up picking up the entire disk, right? So that explains why in this case here, right, for this disk, right, your angle here would be 2 pi, right? Because the first one is theta is equal to 0, right? And then you go right around and then you come back to theta is equal to 2 pi, right? Okay, or a next way to deal with this is once you see the theta going between 0 and 2 pi, it means that you're going right around the circle, right? And you're going to come back, right? Let's continue working on this example, right? So we have your double integral here, right? This function specified inside here, 1 minus x squared plus y squared. And I'm integrating over region R. The region R was specified for me as a set using xy coordinates, right? So the first thing I did is sketch the region. I got that it was a unit disk. And then once I realized it's this disk over here, I need to figure out the expression as a polar rectangle, right? And as I said, your outside radius is 1, so that gives me this 1 over here, right? The inside radius here is 0, so this gives me the 0 over here. You're starting at theta is equal to 0 here, right? And then you go in right around and you come in up to theta is equal to 2 pi, which is this here, right? Okay, so if you're going to convert to polar coordinates, right, you'd want to notice this here is expressed in terms of x and y. You need to re-express it or rewrite it in terms of r and theta, right? So you want to write the region as a polar rectangle, right? Okay, and now that you have that, right, what you're going to do is you're going to use your formula for conversion to polar coordinates, right? Okay, so I use this formula over here to convert my double integral into polar coordinates, right? Okay, so what is this saying? That the x, where I see the x, I'm going to replace by r cos theta. So I replace this x squared over here by r squared cos squared, right? So the x is being replaced by r cos theta. Similarly, y is going to be replaced by r sine theta, so I end up with r squared sine squared theta over here, right? Part of the conversion is I'm going to have an extra r outside here, so I have this extra r outside here, right? And then the limits of integration, right? So I need limits of integration for the r here, integrating with respect to r. And those limits of integration come from the polar rectangle, right? So remember this region that was given to me. I first sketched the region, and then from the sketch I determine the constant values here for the expression as a polar rectangle, right? So for r, the r goes between 0 and 1 over here. So I put 0 and 1 here, right? So the 0 and 1 is coming from the polar rectangle, right? And then for the theta, when I'm integrating with respect to theta, the theta values come from here, 0 and 2 pi, right? Okay, so now that I have that, right, now I go ahead and I do my integration here, right? So first thing I'd want to do is I'd want to simplify, right? Okay, and here what I can do is I can factor out an r squared, so I'd have cos squared plus sine squared, and the cos squared plus sine squared is going to be equal to 1, right? So that's why I end up with this r squared over here, right? Okay, so the cos squared plus sine squared will go to 1, and I end up with this r squared, and now I have this double integral over here, right? Now, while it's in r and theta and so on, it probably looks a little different. At this point, this is really the integration method is just the same as what we did for rectangular or type 1 or type 2, right? Matter of fact, it's closer to rectangular because these are just constants over here and over here, right? Okay, if it was type 1, right, then what you'd have is possible functions here and here, right? But the fact that now this is a polar rectangle, right, and the cases that we would look at in this class is that we'd only have constants here and here, right? Means basically this sort of integral is like the double integral for the rectangular case that we did before, right? Anyway, so how do we do this? Well, first you're going to integrate this inside bracket with respect to r, right? Okay, so what you do is you just multiply this out, so you're going to get r minus r cubed. And then this is just normal integration here with respect to r, right? You integrate the r, you're going to get r squared on 2, you integrate the r cubed, you're going to get r to the 4th on 4. And what you do is you put in the r values, r is equal to 1 and r is equal to 0, right? And when you do that, you're going to get a half minus a quarter here, and then minus 0, right? So you're going to get a quarter over here, right? Okay, so after doing your first integral with respect to r, you just come down to this integral of a single variable here, right? Where your inside here is a quarter. And now this is just straightforward integration, right? You integrate the quarter to get theta on 4. And then when you plug in the 2 pi and the 0, you're going to get 2 pi on 4, which is pi on 2, which is your answer.